Hello and welcome to the introductory video for SDS PAGE, and in this short presentation I'll be covering what is SDS PAGE and what is it used for. So to start off, what is it used for? Well, it isn't really used for much. It's mainly used to denature proteins to make them more linear and to separate proteins based on their size. Okay, so let's begin with SDS, which is sodium dodecyl sulfate, which is this molecule right here. What this molecule does, it has a hydrophobic tail and a hydrophilic head, so it almost acts like a lipid or a solvent. And what this does, it disrupts non-covalent bonding between proteins such as ionic bonding, and it also coats the protein in a negative charge, and this will help make the molecule more linear. This picture here describes the process of how SDS works very clearly. So as we know, proteins in their tertiary or quaternary structure always have this folding with intrinsic electrical charges caused by ionic charges or partial hydrogen bonding. When we apply SDS, the SDS molecules line up against the protein, unraveling it, making it more linear and removing any of these positive charges, therefore coating the whole molecule in a uniform negative charge. Sometimes SDS by itself is not enough to cause the whole molecule to become linear. Therefore, we can add another molecule called DETT or dithiothreatol, and this operates by breaking up the disulfide bridges formed in the protein. And then to break up any hydrogen bonds which can form, we then heat up the protein to approximately 95 degrees for 5 minutes, and this will be enough to break the hydrogen bonds, therefore making the protein linear. So once the proteins are now linear, we then want to separate them based on their length and size. And to do this, we do a process called PAGE, which stands for polyacrylamide gel electrophoresis. This works by using a porous material called polyacrylamide, which when electrical current is passed through the proteins, will cause them to fall from the top of the polyacrylamide to the bottom of the polyacrylamide. Due to the size of these pores, the smaller proteins will fall much quicker to the bottom than the larger proteins. So as the process of PAGE goes on, these blue bands you see here, which is a mixture of the SDS and the proteins, will gradually go to the bottom. The larger proteins would work their way slowly down the column, whereas the smaller proteins will make their way to the bottom faster. And that is the end of the introductory video for SDS PAGE, and in this I covered what is SDS PAGE and what is it used for. So thank you for watching, and continue on to watch the experimental procedure of SDS PAGE. Okay, so the first step is to mix Langley sample buffer solution to your protein sample, and depending on the strength of your Langley buffer sample you're using depends on what ratio you use. So in this video we are using 4x Langley sample buffer, so this means we mix in a 1:4 ratio. Once you do that, you then gently mix and then continue. The next step is to heat your sample at 95 degrees for 5 minutes. Remove the polyacrylamide cast from its packaging and also removing any excess fluid that will be in there. You then remove the comb from the top of the cast. The next step is to fix the polyacrylamide to the cassette. You do this by unclipping the two green bridges either side of the cassette and then placing the polyacrylamide with the tool side facing outwards. You fix it in and then clip the two bridges back together. The next step is to place the cassette into the gel loading tank. When doing so, you must ensure that the red side of the cassette is linked to the red side of the gel loading tank and the black side to the black, as these are the electrodes. Once the cassette is then into place, you then fill the tank with running buffer. To do this, you pour the running buffer into the reservoir created by the cassette and allowing it to overflow. As soon as the reservoir starts overflowing, continue adding until the running buffer reaches the line indicated on the side of the gel loading chamber. The next step is to load the protein ladders into your wells. To do this, you must precisely place the tip of your Gilson pipette into the wells and gently release the protein ladder into it, ensuring that no air bubbles are released. Once the protein ladders are in place, you can then move on to adding your protein samples into your required wells. again ensuring that no air bubbles are released into the fluid. Once all your samples are loaded, you are then ready to continue on with the electrophoresis. To do this, you must then add the lid onto your electrophoresis chamber, again ensuring that the black side goes to the black and the red side goes to the red. Then once everything is connected, you are then ready to move on with electrophoresis. The general rule of thumb is that you use 40 mA per gel you are loading. You will know that a current is successfully flowing when you notice that bubbles are rising from the bottom of the running buffer. Usually the time taken for the electrophoresis to successfully occur is around half an hour.